In this video, I'm going to discuss the elimination reactions known as E1 and E2. So the E1 being the unimolecular reaction and the E2 being the bimolecular reaction. And so what we're doing in these reactions is eliminating usually a hydrogen and a halogen like this. So we're removing that and forming a double bond right here. And so we're forming double bonds between carbons in these elimination reactions. So we'll start with the E1, which is the elimination unimolecular. And so just like in the unimolecular substitution reaction, the first step is going to be our leaving group leaving. And so the electrons from there will move up onto the leaving group. And so the leaving group is now this negative carboanion, and then we're left with not a carboanion, but just an anion, and we're left with this carbocation right here. And so that's the rate limiting step. So this is going to be slow right here because just like with the substitution, we're forming a negative anion and a carbocation, which is going to be very unfavorable. And so that's the slow step right there. But just like with the nucleophilic substitution reaction, the next step is going to be fast. And so this one, we bring in a base that's going to take this hydrogen, and then the electrons from this bond are going to go down here to form that double bond. And so we end up forming our double bond here. And so this one is the fast reaction. It's going to happen pretty much as soon as this carbocation is formed, you're going to have this reaction because these carbocations are very unstable. So this reaction, this part of the reaction here is going to be very favorable. And so we can see here, just looking at the orbital diagram, so we have our base coming in, it's taking this hydrogen right here, and then the electrons from that sp3 bond right there are going to move into this vacant p orbital. They're going to start overlapping with it and form the double bond right here. And so we end up forming this pi bond from those right there, from the vacant p orbital and the sp3 orbital going from this carbon right here to the hydrogen. So we see that the main lobe up here is going to the top lobe of this vacant p orbital, and then this small back lobe here is going into the bottom lobe of the vacant p orbital. And so, of course, this is going to be in competition with SN1. So, like I said, in both cases, we have the leaving group leave first. So that's the first step. That's our slow step right here. So we form the carbocation. And so then if we have the E1 mechanism going on here, we're going to have this right here, this weak base can come and take this. The electrons go down to form the double bond right there. So we have the E1 reaction. And so we end up with this right here after it has taken that hydrogen from it. But we could just as well do this. So we could just as well have this come down and bond to that carbocation there. So we end up with this right here. This is then going to come and take that hydrogen. The electrons will move onto that oxygen, and we end up with this this ethoxy right here, this ethoxy product right here. And so these are in competition. There are ways to sort of try and control for one over the other, but you are going to get a mixture of the products for this. All right, so yeah, like I was saying before, we have the rate limiting step, which is just the leaving group leaving right here. And so we see that this is a very large activation energy to get up to that rate limiting step. But then once we get there, once we get to this right here with the carbocation, then it's fairly easy to get up to that second rate limiting step and come back down to the products here. And so that's why this is a unimolecular reaction, because the the kinetics here is based just on the concentration of this substrate right here. So it's not going to be the base concentration is not really going to contribute to the rate of this reaction. It's going to be dependent only on the substrate here. All right, and so just like with the SN1 reactions though too, we can also have hydride shifts here. And so we have our leaving group, which is this bromine on this secondary carbon. So that's going to leave, the electrons go up there. We form this carbocation here. And so this carbocation is on the secondary carbon, but we have this tertiary carbon right next door. So we can have the hydrogen with its 2 electrons move over to that secondary carbocation so that we can form this more stable tertiary carbocation. And so what that means is we can also end up with 2 different products here. And so, for instance, we could have this come down and take a hydrogen from right here. So we could have this come down and take this hydrogen right here. And then the electrons, well, the electrons are going to move down there to form that double bond. Or we could have the electrons come over here, grab this hydrogen, and have the electrons come down right there. So we could form either one of these products here. And so I have the one here boxed in blue, where if it took this hydrogen right here, and the one boxed in green, where if it took this hydrogen right here. And so it could form either one of those products right there. But again, we can go by Zaitsev's rule, which says that the product with the most substituted double bond will predominate. And so what we see up here, if we use this blue one right here, then we have this tri-substituted double bond. So it has 1, 2, 3 things bound to it, where if we do the green one, we only have the 1 and 2 things bound to it. And so that's di-substituted. And so the di-substituted one is going to be the minor product. It's only going to be about 10%, where the tri-substituted will be the major product here. And we can see the general forms here, where this has the 2 R groups here, which would be this one, and then the other carbon, there's 1 R group, which is right there, where this has 2 R groups on here, which would be this one, and then this other carbon does not have 2 R groups. It's only 2 hydrogens on there. And so in general, we can look at it like this. If it's tetrasubstituted, that's going to be more favorable than the tri-substituted, which would be more favorable than either of these di-substituted right here, whether we have it as the geminal or as the vicinal like this. That's going to be more stable than the mono-substituted. And so we can use Zaitsev's rule to sort of predict what's going to be the major and minor product from these. All right, so now we can look at the E2 reaction, which is the elimination bimolecular. And so on this one, just like with the SN2, we're going to have essentially a double-stepped mechanism happening all at once here rather than happening in 2 separate steps. So this is going to take that hydrogen, the electrons from here are going to move down here to form the double bond. That's going to push the electrons from here up onto the leaving group so that we form our double bond between carbons right here. And so we can, again, control for because, again, this is going to be in competition with the SN2, the nucleophilic substitution bimolecular reaction. But if we have on the substrate, we have these groups here causing the steric hindrance, then the SN2 is going to be too hindered. And so if we have this strong nucleophile here, it's going to come take this hydrogen, the electrons come to form the double bond on here, and then our leaving group leaves right here. And so we end up with the double bond. So we see that the rate of this reaction is dependent on the concentration of both the substrate and the nucleophile or base here. And so in general, our E2 reaction is going to be dependent on the concentration of our substrate and our base on here. So that's why it's bimolecular. So what we're showing up here, this is a second order reaction because the methoxide ion is a strong base as well as a strong nucleophile. So it attacks that alkyl halide faster than the halide can ionize to give a first order reaction. So it's going to attack this hydrogen right here faster than this bromine is just going to leave on its own. And so that's going to make it a second order reaction. So we don't get substitution, so we are not forming this methyl tert butyl ether. That's because the SN2 mechanism is blocked because of the tertiary alkyl halide is too hindered. So this carbon right here is our tertiary carbon, and so it's too hindered by having these two methyl groups here and this methyl group right here. And so when we have the substrate more hindered like this, it's going to favor the E2 reaction over the SN2 reaction. So the observed product is the 2-methyl propene from elimination of HBr. So this is our 2-methyl propene here. So this is our number 1 carbon, our 2 carbon, our 3 carbon that has this methyl group on it. And so the reactivity of the substrate in E2 is going to be, with the tertiary, going to be more favorable than the secondary, which is more favorable than the primary. So the reactivity order reflects the greater stability of the highly substituted double bonds. And so we're again going to be following this Zaitsev's rule here. So I noticed when I got down here that I had this structure right here for the substrate. So this one right here, and this is actually the carbocation, but this is the bimolecular reaction. So we're actually going to want this version of it here. So we have not formed a carbocation. And so what we're going to have is this base here is coming in, and so it's going to attack either one of these hydrogens that are on either side of the bromine here. And so for instance, if it comes down and attacks this hydrogen, then these electrons will go here and will form this product that I have boxed in blue right here. Whereas if it came and attacked this hydrogen, we'd have these come down here, and in either case, we're going to have this bromine leaving in this reaction. So in either case, this bromine is our leaving group. But we can end up forming the double bonds like we have here in this blue one or in this green one here. And we see that with the blue one, we are attacking this hydrogen, this primary hydrogen here, whereas with the green one, we're attacking this secondary hydrogen right here. And so the one that is di-substituted right here is going to be more favorable than the one that is mono-substituted. So again, following that Zaitsev's rule here. And so attacking this green one here is going to be the more favorable reaction. And so yeah, we get those two products there. So this is just an example of this, a particular example of this. So we have this hexane here, this 1-bromo 1-methyl cyclohexane. So we could either have this coming down right here and attacking this hydrogen right there, and the electrons going down to there, or we could have this one right here come attack that hydrogen, the electrons come down right there. And so if we do the green one, we'll form the double bond right there. If we do the blue one, we'll form the double bond right there. And so we see that the blue one, we are attacking this primary hydrogen here, where with the green one, it's the secondary hydrogen here. So the blue one is going to be only di-substituted, so this and this being the carbons substituted on it, whereas with the green one we are going to be tri-substituted. So that's this carbon, and this carbon substituted on that double bond. So that will be the major product. All right, so with the E2 reaction, the stereochemistry is going to be important. So whether we are what's called anti-coplanar or syn-coplanar. So coplanar just meaning that like if we look at the Newman projection here, this hydrogen that this base is going to take, and then the leaving group here are in a single plane. So we have a plane that kind of goes down like this. They're a coplanar. They're in the same plane. And anti just meaning that they are on opposite sides. So we have this hydrogen pointing up and the leaving group pointing down. And so our base is going to come in, take this hydrogen. The electrons are going to move over here to form this pi bond here. And the leaving group is going to leave. And so we have that leave, and we are forming the pi bond here. This can also happen with the syn-coplanar, but it's going to be a lot less likely to happen. And so syn-coplanar, meaning that the hydrogen that's being taken and the leaving group are sort of pointed in the same direction, and coplanar, meaning that they're in the same plane on here. And so this is going to be less likely to happen though, because we have the repulsion of the negatively charged base here and the partial negative on the leaving group, but we also have the eclipse conformation here, which has this torsional strain. So that's the strain between the electrons in this bond right here and the electrons in this bond right here. But this can happen. So we can have that go there, and the electrons will move over to here and over to here to form that pi bond there, and the leaving group will leave. And so you can sort of force this syn-coplanar one if you have, for instance, a syn-coplanar held in a rigid conformation, like on this bicyclic ring system right here, where we can have our base come take this hydrogen, the electrons will move onto this right here, and then those electrons will move onto there, so that we end up with our leaving group here. And so we can force this sort of syn-coplanar geometry onto here. So the E2 is a stereospecific reaction, which means that depending on whether the carbon is S or R, we will get either a trans or cis double bond respectively. And so what we see with the S, so if we kind of so this bromine is our leaving group, so if we kind of turned it down like this, we would end up with the pH sort of pointing in the back here, and the H pointing out towards us. And so this leaving group would leave after this hydrogen is taken. And so the H is going to continue pointing in the same direction as this phenyl group right here. And so we end up with a phenyl group pointing in one direction and the phenyl group pointing in the other direction. So we get the trans isomer right here. Whereas if it's R, now instead of turning around that single bond in the sort of counterclockwise or clockwise, if we were looking at it from that direction, so looking at it from that direction, we now would want to sort of rotate it around counterclockwise, and so we will end up with these phenyl groups pointing in the same direction, and so we get the cis here from this R chiral center, whereas up here with the S we got the trans isomer from that S chiral center. All right, now we can also compare the E1 and E2 reactions. And so it's going to be sort of similar to what we saw with the comparison of the SN1 and the SN2. And so the effect of the base, so the E1, the base strength is unimportant because we are forming that carbocation. So that's sort of the rate limiting step. And once that's formed, taking that hydrogen is going to be very favorable because the very unstable carbocation, and so the base strength is really not that important. Whereas if we want an E2 reaction, we require a strong base because we want to pull the hydrogen off before we have formed the carbocation. And so that's going to be less favorable taking that hydrogen. And so we need something that's a strong base that's going to take that hydrogen more readily, more favorably. So the effect of the solvent, so the E1 requires a good ionizing solvent because again, we're forming the leaving group, which forms the anion, and we're forming that carbocation. So we want a good ionizing solvent, so like a polar protic solvent. So, like water, or maybe like an alcohol, or just a water. So something like that is going to be very good for the E1 elimination reaction, where the E2, the solvent polarity, is not so important. And so, because we're not forming these anions and cations, we're not forming ions, and so being able to stabilize the ions is not as important. We are forming an anion with the leaving group, but it's not forming on its own, and so we are also not forming the carbocation. So the solvent polarity isn't as important. You're probably going to want to tailor it to whatever kind of thing your substrate and base are actually going to dissolve into. And so the effect of the substrate, so with both of them, the tertiary is going to be more favorable than the secondary, which is more favorable than the primary. So the primary will usually not do E1, because if you have just a primary carbon, so we have our R and our carbon here, so this has these H's bound to it, and then our leaving group, it's not going to be very likely that the leaving group will just leave on its own on this primary carbon, because primary carbocations are much more unstable than like tertiary carbocations, for instance. And so the kinetics, as I've already said, so the E1 is based just on the concentration of our substrate, where with the E2 it's based on the concentration of our substrate and the base that's going to be taking the hydrogen from it. And so that's why they're called the unimolecular and bimolecular elimination reactions. So orientation of elimination, so like I've said already, the Zaitsev orientation is going to be the most favored, so the most highly substituted double bond is going to be the one that's the most favored. All right, then the stereochemistry, so the E1, no particular geometry is required for the slow step, where with the E2 we want the coplanar arrangement, usually anti, required for the transition state. So with the E1, we just have the leaving group leaving, and so it doesn't really matter which way it's oriented relative to sort of the neighboring carbon atoms, and so, because we're not having sort of that concerted movement of electrons like we do in the E2 reaction, and so it doesn't really matter what the geometry is during the slow step of the leaving group leaving. But with the E2, as I discussed above, the coplanar arrangement is required, and that's because you're taking that hydrogen, the electrons are going right from that hydrogen down to the double bond, then the electrons from the leaving group are going onto the leaving group and allowing it to leave, and so we need this this coplanar arrangement here for these electrons to sort of move from these lobes here onto the neighboring lobes, so those need to be oriented in the same direction in order to get that to occur. All right, and then the last thing here, the rearrangements. So in E1, the rearrangements are common, so the hydride shifts that will, move like from a tertiary carbon to a secondary carbon in order to put the positive charge on the tertiary carbon, or on whatever the more stable carbocation is. And so we get rearrangements there where E2, there's no rearrangements because the reaction is, pretty much like a concerted reaction where you're taking the hydrogen, the electrons are moving down to the double bond, and then the electrons uh, bonding to the leaving group are going to the leaving group sort of all at the same time. And so there's not really any time for a rearrangement to occur there. But anyway, that was the elimination reactions. Like I said in an earlier video about the substitutions, that these are in competition with these elimination reactions. So you're not going to get just pure elimination products or pure uh, substitution products. You're going to get a mixture of them. And in fact, in the next video, I'm going to go over some of the things that you can take into consideration when trying to predict what's going to be at least the major product between, like the SN1 and E1, or between the SN2 and E2. So that will be in the next video. But anyway, I hope you found this one helpful, and I will see you in the next one.